So, welcome to this class on hardware security. Today we shall be studying about elliptic curves, which is a kind of de facto public key crypto system, and we shall be trying to understand eventually the hardware design or how to do a hardware architecture for this algorithm. So, we shall be trying to start with some of the basics and trying to introduce them in the class. So, in today's class we shall be covering, or we shall be getting an introduction to elliptic curves. We shall be trying to understand the elliptic curve arithmetic. We shall be trying to understand how point addition and point doubling, which are essentially two important operations in the elliptic curve group, are being performed. We shall be trying to understand the concept of projective coordinates, which are essentially used to reduce the computations which are required to perform elliptic curve operations. And in particular, we shall be trying to look into characteristic two elliptic curves, which are very conducive for hardware design. So, let me start with an example which is essentially trying to explain an old method which is called as the method of Diophantus. So, in this example or in this sort of question, we inquire what is the number of balls that may be piled as a square pyramid and also rearranged into a square array. Okay. So, basically, like we are basically asking that what is the number of balls that may be piled up in both of these arrangements. So, you can either arrange these balls, like as a square pyramid. That means it's essentially a pyramid where the top essentially has got, say, one square number of balls. In the second layer you have got two square number of balls. In the third layer you have got three square number of balls, and so on. If the height is x of the pyramid, then you have got 1 square plus 2 square plus 3 square plus so on till x square number of balls. And likewise, you can also rearrange them in the form of a square. So, therefore, if y is the side of the square, then you have got y square number of balls in this arrangement. So, since they are equinumerous, that means you are essentially arranging the same number of balls, then that would mean that in both the arrangements the number of balls are same, right. So, therefore, we can easily write this equality, that means y 1 square plus 2 square plus so on till x square, which is equal to x into x plus 1 into 2x plus 1 by 6 is equal to y square. Okay. So, these kind of equations, which are essentially quadratic in y and also cubic in x, essentially are what are called as elliptic curves. Okay. Of course, there are a lot of definitions which have been developed over the years on elliptic curves, but this is the general form of the curve. Okay. So, therefore, right, in order to solve this problem or this kind of problem or this class of problem, there is a very famous method which is also an old method, an ancient method, which is due to Diophantus. Okay, or is often referred to as the Diophantus method. So, I will be first starting with an explanation on how it works, and gradually you will understand that how closely it is connected to the elliptic curve operations. Okay. So, therefore, the graphical representation of this curve is often of this form. So, you can see that it is quadratic with respect to y. That means it will be symmetric over the x axis. Okay. So, therefore, this is a form of the curve, and you can see that typically, right, this is essentially, it looks like as if it is a cup with a single handle. Okay. So, and this is essentially or this curve or nature of the curves of this nature are called as elliptic curves. Okay. So, therefore, right, I mean, if you take this curve and you can see that there is typically the number of handles that you have, right, is essentially also a very important feature of this curve. Okay. So, typically in this in the elliptic curves that we use for cryptography, there are one such handles, or there is one such lobe, okay, which is essentially belong to this curve. So, now the question is, how do we solve the problem that we have in hand? Okay, that means the problem of determining the number of balls. So, remember the number of balls has to be an integer, right. Of course, the number of balls has to be an integer. So, therefore, right, the way we start is essentially from trivial solutions to this equation. So, you can easily inspect that in the curve that we essentially saw, 0 0 are trivial solutions. Okay. So, if we just reflect back at the equation, right, the equation was y square equal to x into x plus 1 into 2x plus 1 by 6, right. So, if I may write down the equation was y square equal to x into x plus 1 into 2x plus 1 by 6. Okay. So, you can easily see that 0 and 0 are solutions to this this equation. So 0 0 is a trivial solution, right? 0 comma 0 is a trivial solution. Likewise, you can also see that 1 comma 1 is also a trivial solution. 1 comma 1 is also a trivial solution. So if I plug in 1 here, this is 1, left hand side is 1, and the right hand side is 1 into 2 into 3, that is 6 divided by 6, which is also 1. So 1 comma 1 is also a trivial solution of this equation. So now what we will do is that we will basically draw a straight line through these 2 points, that is 0 0 and 1 1. Okay. So you can easily see that in that case, right, the line is nothing but y equal to x. Okay. So that means, like, if I believe that in the curve that we have, okay, so we basically kind of say consider that your curve is something like this, right? I take this point 0 0 and I take the point 1 1 and I draw a straight line through these 2 points. Okay. So that means this is my 0 0 point and this is my 1 1 point, and I draw a straight line, and this straight line is y equal to x. Okay. So now you can basically see that since this equation is cubic with respect to x, so if I plug in y equal to x into the curve equation and I do a few rearrangements, then you will get this equation, which is x cube minus 3 by 2 x squared plus 1 by 2 x. Okay. So this essentially or this equation is cubic with respect to x, which means that there are 3 possible roots. So we already know that 0 0 and 1 1 are 2 roots, that means x equal to 0 and x equal to 1 are already 2 roots. We need to determine the third root. Okay. So therefore, from the theory of equations, we add up the roots, that means we do like 1 plus 0 plus x, that means we add up the 3 roots of this equation, then that should be the negative of this coefficient. Okay. That means it is equal to 3 by 2, and therefore we easily can obtain that x is equal to half. Okay. Now you note that x equal to half implies y equal to half. Okay. And therefore the number of balls, right, is y squared. So you can easily see that since y is a fraction, that is not the solution that where we should stop. Okay. But at the same time, this is nevertheless a non-trivial root of the equation. So you can similarly generate non-trivial roots. So what you can do is you can start with half comma half. Okay, and you can easily see that if half comma half is one root, then since the curve is symmetric over the x axis, then that means, like, if x comma y is a root of this curve, then that would also imply that x comma minus y is also a root on the curve. Okay, is also a point on the curve. So that means, like, half comma minus half is also a point on the curve. Okay. So now we can essentially take half comma minus half and continue this exercise. Okay. So that is essentially the broad idea of Diophantous method. So let us see if we do that, then what happens. So therefore, right, if I take now a straight line through half minus half and 1 comma 1, then my equation in this case is y equal to 3x minus 2. Okay. So now I take y equal to 3x minus 2 and again plug it into the curve. That means I intersect the straight line with the curve. Now I get an equation which is x cube minus 51 by 2 x squared plus some terms. Okay. Again I apply the theory of equations. I know that half and 1 are 2 roots. I need to obtain the third root. Okay. So therefore I add half with 1 with x, which is my unknown root, and that is equal to the negative of this coefficient, which is 51 by 2. Okay. So now I obtain an integral value of x. That means in this case x is equal to 24. Okay. And I am lucky that this is an integer, and therefore I obtain that y is equal to 70. So I can tell that y equal or y square, which is 4900, is the number of balls, okay, which can be arranged in both of this manner, So while this problem can have its own implication and statement, what essentially I am trying to kind of illustrate out of this example is that if you take curves of this nature, then you can essentially have this nice like technique of starting with trivial roots and obtaining further points on the curve by using this technique of like drawing straight lines and finding out the third point of intersection. Okay. So this is essentially precisely like one of the techniques which leads to something which is called as the chord and tangent rule in context to elliptic curve cryptography or elliptic curves in general. Okay. So therefore, right, I mean, elliptic curves in cryptography were, just to give a little bit of background, was essentially kind of made popular in around 1985, and essentially forms the basic basic structure on which elliptic curve cryptography has been designed. Okay. So there is a problem in this case, or essentially a hard problem, like all public key cryptographic systems like this also relies on the notion of some hard problems, and the notion is called as a discrete log problem or discrete logarithmic problem on elliptic curves, which is believed to be more difficult than corresponding problems in the multiplicative groups of non-zero elements of the underlying finite fields. Okay. And therefore, elliptic curve cryptography can also often operate with much shorter keys compared to the other counterparts like say RSA. Okay. And that is essentially precisely the reason why elliptic curve cryptography is essentially kind of has become very popular and is often considered as a de facto public key crypto systems for many like resource constrained environments. Okay. Because you can essentially operate with shorter key sizes, and therefore you can do the arithmetic with smaller finite field operations. Also, right, if you want performance, right, this also can give you quite fast operations, because again precisely because of the same reason, and therefore you can also have high performance public key cryptography which can be used in data centers and cloud and other kind of infrastructure where performance is a key criteria. So therefore, right, let me try to look at now and more formally into a form of elliptic curve. Again, this is a toy example. So consider that I write y squared equal to x cube plus 2x plus 3. So you see that this is precisely the curve that, or form of curve, that we have been seeing in context of the Diophantous example. But one thing that we need to kind of keep in mind when we are considering elliptic curve cryptography is that like that it often operates on finite fields. Okay, that means that the basic elements, okay, or the basic points, or the basic points means like the x coordinate and the y coordinate of the points, they often belong to finite fields. Okay. So therefore, right, I mean, let me take an example of a very toy finite field in this case, which is say modulo p field, that means say zp. Okay. So zp would imply that my elements can be 0, 1, 2, 3 and 4. Okay. So therefore, in this case, since the space is small, we can see that whether like what are the possible points on the curve. Okay. So therefore, let me start with x equal to 0. You see that if I plug in x equal to 0, I get y square equal to 3, and it turns out that with modulo 5 there are no solutions of y, that means there are no solutions of y which belongs to 0, 1, 2, 3 and 4, which if I square I get 3. Okay. That is because 3 is a non-quadratic residue. Okay. So it is not a quadratic residue in this field. So I don't get any solution with x equal to 0. I start with x equal to 1, I get y square equal to 6. It turns out that there are two solutions. Okay. So therefore, in this case either y is equal to 1 or y equal to 4. Likewise, I plug in x equal to 2, I get y square equal to 15, and 15 is essentially 0 in this case, and therefore y is equal to 0 mod 5. Okay. Likewise, if I plug in x equal to 3, then y square is equal to 36, which is equal to 1. And this implies that y is equal to 1 comma 4 modulo 5, and likewise x equal to 4 also leads to y equal to 0 modulo 5. So that means the points on the curve, or I would say like the finite points on the curve, okay, are 1 comma 1, 1 comma 4, 2 comma 0, 3 comma 1, 3 comma 4 and 4 comma 0. So the elliptic curve, although we are drawing as a continuous line, is actually an array of points, okay, or discrete points. Along with it, we also define a point at infinity, which I will be briefing very soon or detailing very soon, just giving an idea about the point at infinity, is also another point which we believe is at the top of the Cartesian coordinate or also at the below of the Cartesian coordinate. Okay. So this is often called as the point O in context to elliptic curves. Okay. So therefore, right, I mean, this is a very important point. So therefore, whenever we consider elliptic curves, right, we essentially consider some finite points and also one infinite point. Okay. Together they define what is called as the elliptic curve group. Okay. And now what we essentially try to formalize is essentially a problem which is analogous to the discrete log problem in context to like normal finite field operations, which we call as the elliptic curve discrete log problem or the ECDLP problem, which is believed to be a hard problem if the parameters are properly chosen. Okay. So now we basically are all set to essentially define an elliptic curves. So therefore, elliptic curves over a field K is a non-singular cubic curve. So, I will be again defining what non-singular means at the end of this class. Is that is a non-singular cubic curve in two variables f(x), y equal to 0 with a rational point which may be a point at infinity. Okay. So, therefore, I mean if we just ignore a few terms that we mentioned here, the basic idea is that it's essentially a cubic curve. That means it's a cubic curve with respect to x, quadratic curve with respect to y. It is a non-singular curve which I will be defining shortly, and it has got it has got some finite points and also a point at infinity. Okay. Together they are called as an elliptic curve. There are different elliptic curves that you can define, but what we will be considering here in this course on hardware security is essentially elliptic curves which are defined on characteristic prime fields and also characteristic 2 fields. Okay. So, typically these are the two popular alternatives which are used in hardware architectures. They either belong to GFP, that means the underlying field is either GFP or GF2 to the power of m. Okay. So, the architecture that we will be studying in details will be on GF2 to the power of m, simply because they are more conducive for efficient architectures. Okay. Okay. So, therefore, write elliptic curves for groups are examined with the underlying fields of Fp and also F2 to the power of m, which is a binary representation with 2 to the power of m elements. Okay. So, now we essentially let me take an elliptic curve of this nature. So, it is equal to say y squared equal to x cube plus ax plus b. So, this is a general form of the elliptic curve which is defined on a, so is essentially a plane curve defined by an equation of this form, and it can look, these are various curves that we have taken, say y squared equal to x cube minus 1, y squared equal to x cube plus 1, y squared equal to x cube minus 3x plus 3, y squared equal to x cube minus 4x, y squared equal to x cube minus x. So, you can take different curves of this nature by choosing different values of a and b, and it would be a fun exercise kind of to plot these curves and see how they look like. Okay. So, you can see sometimes this lobe is kind of separated from this part, sometimes like it is connected as well. So, it is very interesting to see how this curve kind of varies depending upon the choice of a and b. Okay. One thing you should always keep in mind is that this is not a continuous curve if you define this over finite fields. In that case, these are discrete points. So, there is a general form of the curve which is called as the Weierstrass equation, from which all these curves are derived. Okay. So, this is a two variable equation f(x), y equal to 0, and this looks like this: y squared plus a1 xy plus a3y, which is equal to x cube plus a2 x squared plus a4 x plus a6. Okay. So, now what we will be trying to look into is that depending upon the characteristic of the underlying finite field, this curve can take various forms. Okay. So, therefore, right, what I mean is that sometimes these curves can be of, as I said, the underlying field can be an FP field, which is a prime field. Okay. And it can have different characteristic. Okay. So, if you remember characteristic, right, then that means that the minimum number of elements, that are number of times I need to add 1 in that field to get 0. Okay. So, the characteristic can be 2, can be 3, can be any other thing. So, we will see that how depending upon the characteristic, the form of the curve also differs. Okay. So, here are some examples. So, you can start doing this, that is, I will not go into too many details about these derivations, but these are something that you can also verify subsequently. Is that suppose let me state that if the characteristic field is not 2, okay, that means the characteristic is not 2, that means I can do this operation. What I can do is that I can take this equation and I can rewrite it in this form. Okay. So, here you see that I have divided by 2 certain terms. This division is legal here or is allowed here simply because the characteristic is not 2. If the characteristic was 2, then I cannot do this division, because in that case 2 is equivalent to 0 and I cannot divide by 0. Okay. But here, since the characteristic is not 2, I am free to do this division, and you can easily verify that this is exactly the same equation as this equation, except that I have added few terms and I have kind of adjusted few terms. Okay. So, I leave it to as an exercise to verify that this equation is essentially exactly equal to the Weierstrass equation. Okay. So, once you can write, if you write this in this format, then I can take this part which is inside this square and raised to the power of 2 and replace it by a new y dash, okay, or y1. So, therefore, I get y1 square, which is equal to x cube plus this is a new constant, I write this as a2 dash, plus this is again a new constant, say a4 dash, although it's the same in this case, and I write this as a6 dash. Okay. So you see that the curve, right, essentially kind of transforms into a simpler equation because of this assumption that the characteristic field is not 2. Okay. I can make a further assumption that the characteristic is neither 2 nor 3. So that means now division by 3 is also allowed. Okay. So if I therefore plug in, like x1 equal to x plus a2 dash by 3, and like if I substitute in this case, then I will get the equation further simplified into this form, and this is a very common form which is often used in several standards. Okay. So that is y squared equal to x cube plus x plus p. But remember that whenever this equation form comes, then it is implicitly assumed that the characteristic is neither 2 nor 3. Only then we get this form of the equation. If the characteristic is 2, then we get a different form, as we will see subsequently. Okay. So now let us assume that the characteristic is neither 2 and neither 3, and without loss of generality, let us try to define an elliptic curve group and also some operations on the elliptic curve group, because we need to do at the end of the day arithmetic based on using which we will be doing our cryptographic operations. So therefore, right, as I already mentioned, that the elliptic curve therefore over the field L will consist of a point at infinity along with some points x comma y which satisfies this curve. So this x1 comma y are taken from L square, that means x belongs to the field L, y also belongs to the field L, and they are satisfying this equation, that is y square plus some terms equal to x cube plus some terms, and this x comma y is a point on the curve. So with this we call as finite points on the curve, and this is the point at infinity. So why do we add the point at infinity? Is that it is often, like just we can understand in this way that it is useful to add the point at infinity. Okay. Apparently the point is, you can imagine that is sitting at the top of the y axis, and also is kind of a point which is very far away from this coordinate system, but the introduction of the point at infinity essentially completes the definition of my group. Okay. Without it I cannot define the group. So that is essentially you can also you conceive in this way, it is essentially nothing but the identity of my, or it is essentially my 0 element of the group. Okay. So this notion will be clear very soon. Okay. So it is kind of sitting at the top and also the bottom of the y axis. Okay. So therefore, right, let us try to define the group, and this is a quick recapitulation of what abelian groups essentially imply. So if I consider 2 points p comma q which belongs to EFP, so EFP means that now I am defining an elliptic curve on the finite fields FP. Okay. So similarly I can define it on any finite field. Okay. So there is a third point which is denoted by p plus q. So now you see that I am taking 2 points on the elliptic curve, say p and q, and I am trying to define an operation which is plus. So note that this operation plus is not a normal plus. Okay. So it is essentially a plus, or plus symbolizes some operation. Okay. So you can, if you are confused or if you don't want plus, you can very well replace it by any notation. Okay. So therefore, right, I want to define some p operation with q, so that I again get another point which is r, which also belongs to the field. Okay. Belongs to the elliptic curve. So here you see that the Diophantous method is exactly the same, because I start with 2 points p and q and I want to obtain a third point on the curve. Okay. So therefore, right, if I want to define an abelian group, then I need these properties. That means I need the property of commutativity. That means if I take p and q, the operation should be same as p plus q is equal to q plus p. It should be associative. That means p plus q then added with r should be same as p plus with q and r. Okay. Similarly, right, there should be an identity element which exists. That means p plus a point O should be equal to O plus p, and I should get that p, and there should exist inverse. That means p plus minus p should be equal to O. Okay. So all these things has to be satisfied for us to have a complete definition of what is called as an abelian group. So if I start with an elliptic curve picture, therefore, so this is essentially an elliptic curve equation. So you see that it is y squared equal to x cube minus x plus 1, and we want to have so we want to define this operation plus. Okay. So therefore, right, let me start with 2 points on the elliptic curves, say p1 and p2, and I want to define what is p1 plus p2. Okay. So the usual way it is done is again by applying a chord through p1 and p2. So again remember that since this is a cubic equation in x, this intersects the curve on a third point, and now I take this point and I reflect this point. Okay, so if I reflect this point, I get this point which is P3. So this P3 is essentially nothing but the addition of P1 and P2. Okay, from Diophantous technique or in general also you easily understand that P3 should be a point on the curve. Okay. So likewise, so now you can essentially are all set to obtain some details about about how the addition works, and we will be kind of seeing how how you can get these equations. Okay, so now we essentially can derive the equations for doing this addition operation. So what I essentially kind of said, now we can see in a more mathematical way. So we can take P and Q. So imagine that the point P is nothing but x1 comma y1. So the point P is let me try to write it here. So so the point P essentially is this point. Okay, so let me write this point as x1 comma y1, and likewise this is my point Q, which is nothing but x2 comma y2. Okay. So we draw a chord through these 2 points, and therefore this is your minus P plus Q. If I reflect this, I get P plus Q. Okay. So what we are interested is now is in the coordinates of P plus Q. Okay. That means how do I get P plus Q basically. So you can easily understand from the simple theory of coordinate geometry, that is the slope of this curve. So this is suppose m. Okay. So the slope of the straight line is m, which means that the straight line equation is nothing but y equal to m x minus x1 plus y1, because the straight line passes through x1 and y1. So therefore m is nothing but y2 minus y1 divided by x2 minus x1. Note that we are assuming here that the point P and Q are distinct. If the point P and Q are distinct, then this m is not defined. So therefore we cannot apply this equation. Okay. So now if I want to find out the intersection with E, then what we will do is that we will take this straight line y equal to mx minus x1 plus y1 and plug it into the curve equation, and therefore write with little bit of adjustment again I will get this equation. I will get like x cube minus m square x squared plus some terms, this will be equal to 0. So you can see that I have replaced y with this equation, that is mx minus x1 plus y1. So therefore right now again if I arrange these terms, then and I know that since there are 3 roots of this curve, so 2 roots are already x1 and x2, I want to obtain this root. So suppose this root is x3, which is essentially the same as the x coordinate of this inverse, then I can write that x3 plus x1 plus x2 is nothing but the negative or negation of minus m square, which is m square. So therefore I can obtain x3, which is equal to m square minus x1 minus x2, and from there I can obtain y3, and I can negate y3 to get this equation, I mean this coordinate. Okay. So you can easily see that I can essentially obtain say minus of y3 is equal to m of x minus x1. So m is nothing but as we have already obtained, that is m into x minus x1 plus, so in this case this x will be replaced by x3. Okay. So x minus x3 plus y1. Okay. So therefore I will get y3 as m x1 minus x3 minus y1. Okay. So you can, I hope you understand that if x3, if this point is x3 comma minus y3, then this point is, which I am inverting over the x axis, is x3 comma y3. Okay. So this you can easily understand by if I can take a straight line. So this line is say x equal to say h, right, and I draw it with the curve. That means my curve is y squared equal to x cube plus ax plus b. So if I plug in x equal to h here, then I get y square equal to h cube plus h plus b. Okay. So that means there are 2 roots of this equation. Okay. So I already know that. So the idea is that I mean, since this is symmetric over the x axis, that means if y is a root, then minus y is also a root. Okay. So that means like if x3 comma y3 is a root, then x3 comma minus y3 is the also falling on the curve, and that is the inverse of that point. Okay. So that way you can calculate the inverse. So therefore the first thing that we did here was obtain this point, and then we kind of reflected this point and obtained the negative, which is essentially nothing but the addition of p and q. Okay. So this is a simple operation, and you can essentially extend this also to the case where x and p and q are same. Okay. That means in that case we will not draw, we cannot obtain m in the way we saw, but we can obtain m by taking derivative or obtaining the differential at the point x comma y. So now if I derivate my curve, then I can obtain 2y dy by dx, which is equal to 3x square plus a, and therefore m, which is the slope, is nothing but by dy by dx, and at the point x1 comma y1. So if I obtain this at the point x1 comma y1, then this is equal to 3x1 squared plus a divided by 2y1. Okay. So if we are particular, then we should actually write here that this derivative is taken at the point x1 comma y1. Okay. So then this is equal to 3x1 square plus a divided by 2y1, and again we apply the same thing. So I know, but in this case there are two roots and both of them are same. So therefore that is x1 plus x1, that is 2x1. Note that the characteristic is neither 2 nor 3, so I can obtain 2x1, and therefore write my x3 is nothing but m square minus 2x1. Okay. So likewise I can obtain y3 exactly like what we saw in the previous case, and we can obtain these equations. Okay. So now the question is, right, what happens when one of the points is the point infinity or is at O. Okay. So there you can easily see that when we consider that we essentially okay. So essentially, right, okay. So what we see therefore, right, once we have derived the point at addition and the point at doubling, but we remember that we have been operating on finite points, but as I mentioned that in the curve there is also a point at infinity on which also I need to do these operations. So what essentially happens if one of these points is that point, that means it is the point at infinity. So that means like what happens when P2 is equal to infinity or is a point O. Okay. So let us see that. So therefore if I want to add with O, remember O is a point which is kind of at the conceived to be as at the top and at the bottom both, so it's kind of as a point of infinity. So therefore, right, if I take a point say P1 and if I want to add with O, then the way we do that is as if like drawing a vertical line through P point P1. Okay. So therefore it is assumed that I am essentially trying to kind of draw a line which goes through P1 and the point at infinity. So that essentially you can imagine is as if like a vertical line. So therefore this will cut the curve at this point, which is essentially nothing but minus of P1. Okay. So there are minus of P1, and therefore if I reflect it back, I get back P1. So that also defines like what I need in my definition for elliptic curve group. That means if I add P1 with O, I will get P1. Okay. So likewise, right, you can also imagine that if I take P1 and if I add with minus of P1, which is essentially this point, then also it will intersect at the point O. Okay. So that also defines that that I have got an inverse. Okay. That means inverse also exists. So therefore, right, the point O essentially kind of completes the definition of what is required in an abelian group. So now you have got some points that are like finite fields on the curve and also like the point at infinity, which is O, and therefore you are all set to define your elliptic curve operations. Okay. You have got a group on which you have also defined two operations like addition and doubling through which you can do your computations. Okay. So let me stop here, and we will continue from this point in the next class where we will try to look at some more details about elliptic curves. So thank you for your attention.